Next is Etienne Dilocker from Weaviate.
Cool, thank you. So this was originally a 25-minute talk that I did for the AI conference, and I have about 8 minutes, so we need to speed run this. Naturally, first thing I did was add a new slide, because why not? Okay, but the talk was actually originally about running billion scale use cases with Weaviate, and two specific ones that want to share more about. One is in e-commerce, the other is email RAG, and this is kind of they kind of represent sort of the two big areas of use cases. One being search, semantic search, and the other being RAG. So if you haven't heard of Weaviate, shout out to Sam Stolingha, sorry for butchering your last name, who did the first talk and already gave you a live demo. I don't even have a live demo of Weaviate with me, so thank you for doing that. So into the cases, the first one of those cases is e-commerce search. So you can think of this like this beautiful Gen AI kind of front end here, where you just have this search bar in the center. You enter your query, whatever that would be. So for example, it could be something like a colorful summer dress or a professional video camera, and all of those search queries would go against one data set. So you would not know anything about sort of what narrows down the query, other than if the user maybe specifies a category or so. And this kind of data set is massive. And at the billion scale, it's not just massive in size, but you also have a lot of updates, a lot of deletes, so it's constantly changing. And for those of you who've worked with vector search before, you might know that can be a bit of an issue. To just handle the amount of scale and the amount of throughput and still do this at low latency, we're using HNSW, which is, if you've heard of this before, it's an in-memory graph-based index, which is great. It's fast. It's super high throughput, super low latency, but it requires you to keep the vectors in memory, which comes at a cost. And before, in Sam's example, you needed 16 gigabyte on your laptop. How about 55 terabytes, which is 10 million with a standard OpenAI embedding. So that's quite a lot. So can we get this down? Yes, we can, by using product quantization, which is a compression technique that can reduce the memory footprint quite a bit, in this case, 8-fold. It's lossful, so it drops quality, but then you can re-rank it again against the full length vector embeddings on disk, and therefore kind of you have this sort of hybrid in memory and disk index, get the cost down a bit, and keep the accuracy high. Next big question is, how do we even deal with so many deletes? Like in this case, I think we peaked at 100 million delete in a single day, and our SREs were definitely sweating that day. How do you do that in HNSW in general? Can HNSW even do this? There are posts out there, blog posts out there that would say it can't. Well, Weaviate's HNSW implementation can, because we have this sort of in-place batch repair job that continuously rebuilds, or not rebuilds, but repairs the graph and keeps the graph integrity. And therefore, if you look at this kind of accuracy graph over time on a data set that's constantly sort of being partially replaced, you can see at the top, like the orange or green lines, they stay pretty high, and more importantly, like yes, there's a bit of fluctuation, but it never doesn't degrade over time, which is pretty cool. So in summary, the first half of the speedrun, the first use case, this use case, billion scale, 10 billion or so objects, uses a lot of CPU for this in-memory graph index HNSW, costs a lot of time to build this graph and also to constantly repair it for the deletes. It runs in memory, but we managed to get the memory footprint down quite a bit by using compression. And then, of course, it's a database, so you have stuff on disk. As you're seeing, we're not using cloud storage here, but that is mainly in contrast to the other use case, which, quick, I really don't have time for this question. I'm going to do it anyway. Anyone using the email client Superhuman? Yes, thank you. At least one.
I was, but I showed way now.
Okay, so Superhuman is a pretty cool email client, and it has this Ask AI feature, which we see popping up everywhere. Pretty much everything that deals with content has these Ask AI kind of AI assistants, and really what that is RAG. And if we're using Superhuman as the example, you do search on your own mailbox, and you definitely don't want someone else to do search on your mailbox. So, and if you think of every single Superhuman user, that's basically a massive multi-tenant case. And basically, instead of this single data set, you have a lot of them. And then you would send a query like, hey, when does my flight out of SFO leave? But Weaviate, in this case, already knows who you are because you're searching your mailbox. So still billion scale, kind of the similar scale as before, but we narrow it down. So it's almost more like we have 1,000,000 scales or so. And that is kind of what this looks like. And this also brings us to this imbalance between writes and reads, because most of you will probably get at least one email a day or so. If you don't, then I'm jealous. And how often do you use these AI assistants? They're super valuable, but you don't use them as often as you get emails, I guess. So you have this sort of imbalance between reads and writes, which is something that we can optimize for. Another sort of interesting thing is just this natural long tail distribution. You have a lot of very small users, and you have some very large users. And then another sort of pattern, oh no, sorry, not another pattern yet, but what this allows us to do is use a completely different index. So in this case, we're using what's called in Weaviate the flat index, which is a disk-based index. It's very simple. It's basically, you can think of it like a column-based index in a column-based database, which is optimized for basically a linear scan on there. And because the data set size is so small, that is actually still pretty efficient. And then what we're doing is we're also shoving quantization onto this index, in this case, binary quantization, this time not to get the memory footprint down because it's already running on disk, but to get just the size down, and therefore doing a linear scan is also faster. So again, sort of working with these kind of tricks to optimize this. And then in the sort of 1 to 5 million objects, which was a large scale a couple of years ago and is now pretty much a tiny scale, so that we can run it sort of 1 million times over and over again. Another one of those natural patterns is the activity. Not everyone is active at the same time. There's less email activity over the weekend, especially Superhuman. I think it's a lot of commercial customers. So that is also something that we can make use of. In very simple terms, we can just say, if we need something right away, if we want to use it and we need it hot, we need it fast, we put it in memory. If not, we just leave it on disk. And if we don't use it at all, we could even shove it onto cloud storage, which makes it even cheaper. And then in summary, that means in this use case, we basically almost don't need any CPUs. I mean, we do, but very few, because it's pretty much I/O bound and no longer disk bound. We use a lot less memory. Memory acts more as a cache, basically, because of course anything that's disk based, you always have page cache, so that helps make it faster. And then really SSDs are do the heavy lifting here. And we use cold storage, cloud storage, basically to offload everything that's inactive. And now you might ask, like, so why is SSD the one that's most used? Why not cold storage? And I think that's a great question. So what is next? This is a tiny piece of our roadmap, but it's kind of a nice slide. Working on full separation of storage and compute, where the cold storage really becomes the source of truth. And we're not just offloading it when we're not using it, but we're completely separating the read path and the write path. And then in the example of Superhuman, this makes a ton of sense because you get a lot more emails, but you don't query as much. So you don't have the right side, which is kind of the expensive side, where you have the SSD disks and the memory to cache it. You don't have to keep your cache hot for something that's currently not being used, but you still want it to be durable and persistent, of course, which is why it goes straight into S3. So in recap, 2 billion scale use cases, both kind of the same. They require real-time latencies, but they're very different. The e-commerce case is like this one massive single-tenant data set. We need this in-memory index, which requires a lot of memory. We use compression to get it down a bit. And on the other hand, we have the email rack case, which is basically a series of hundreds of thousands of small partitions in the data set. But in some, it's also a billion-scale use case, and it also requires the same latencies, but we don't require sort of the low latency, high throughput index for it, which makes the whole thing then cheaper to run. So how can you apply these learnings to your own use case? I would say the first question to ask is, are you the e-commerce case, or are you the Superhuman case, where you basically have these natural partitions in your data set? And if you do, then that should be, everything else falls into place, basically, once you make that kind of decision. So are you doing RAG, or are you doing semantic search? That often can already answer that kind of question. That was it from me. Are we out of time? Okay, cool. Okay, then we're not going for the bonus slide. Thank you.
Good job.